So in this case, with an access control list, it's more efficient because all you have to do is add a new entry for object 4. So it's going to take order of n times because you have to create for each user information. Okay? Whereas if you want to do it on a capability list for a new object you are creating, you have to go through each user's records, scan through all the current objects they have access to, and then append or add information about object 4. So there could be n users, and for each user you have to spend m time because like there are m objects already. So you want to add a new object, you want to add those entries by going through all this list. So it takes n times m complexity, right? So you see, depending on what you want to do and on what you want to do, either an access control list or capability list, the kind of complexity could be different.
Which one is more often used?
It depends on the operating system. Some operating systems use access control lists, like Unix uses access control lists. There's something called, I came across one operating system that uses capability list. Tenenbaum, you have heard of Tenenbaum? He developed that operating system. And that uses capability list. Okay? Alright, so file system. So that is what you're going to do now. So again, a file system represents how information, basically files, are stored in your disk, right? So if you have a hard disk, you have to really kind of what you call format it and then create all the partitions to store the files. Now, normally operating systems do a hierarchical approach where you have directories, subdirectories, and so on, and then eventually you have your files, right? So that's the practice. Okay, so files are normally associated with permissions. So if a user wants to do something on a file, it's the responsibility of the operating system to check whether the user has permissions to do certain things on the file. So again, you will focus more on Unix here, and that's your second project also. So in Unix we have three kinds of users. Okay? One is, for example, you have a file, you create a file, it has kind of three levels of users. One is the owner of the file, whoever creates it. Remember Unix, I said in the previous class, uses what? A discretionary access control model, which means the owner of the file can decide what permissions everyone else has on the file. Okay, it's up to the discretion of the creator or owner of the file. Okay. So you have three kinds of users: the owner, the group to which he belongs to. So every other user is that group to which he belongs to, the owner belongs to, and others. Okay, so everyone outside that group will fall in the others category. So the owner, the group to which he belongs to, and everyone outside the group. So he can set permissions for these three kinds of users. Okay? And again, there could be three kinds of permissions: read, write, execute. So what we are going to see is how to set those permissions for a file. So it's a little math here. We kind of weight the three things. Read, say, gets a value of 4. Write, 2. Execute. This one's basically exponents of 2. 1, 2, and 4. Okay? So there's a command called chmod. If you have worked already on project 2, we should have used it. So chmod is kind of a Unix command to change the access permissions on file. So you come up with, say, some numbers and then the file name. So how to come up with these numbers? So let's say I want to, and the file name is say a.text. Let's say I want to have all the three read, write, execute on that file for the user or the owner, and then read and execute permission on for the others, for the group, and just a read permission for others. So they are in this order. The first number represents the permissions for the owner, the second number represents the permissions for the group, the third represents the permission for the others. Okay? So if you want to set up read, write, execute permissions for the owner, all the three, basically add all the three numbers, 4 plus 2 plus 1, so 7. If you want to set up read and execute for the group, read and execute is 4 plus 1, that's how you get 5. If you want to set up only read permission to others, 4. Okay, so that's how those three numbers come. Very simple. Okay, so let's do one more. If you want to set read, write, execute for Warner, 7. Read and write for group, 4 plus 2, 6. And no permission to others, which means the others outside the group cannot do anything on the file, they get 0. Okay, so that's how it's set.
One more time.
If you want to set, say, read, write, execute for the order of the files, so read, write, execute, all the three should be there, so 4 plus 2 plus 1 is 7. If you want to do read and write permissions to the group, so read and write, so 4 plus 2 is 6. And you don't want to give any of these three permissions to others, the third group, so you have a 0. If you want to give them, say, execute permission, you put a 1. If you want to give them just a read permission, you get 4 and so on. Here. Now, like files in Unix, even the folders have permissions.
Dr. Mac, before you move on, what is it going to have numbers for the permissions? So you can just do chmod plus x, whatever.
Yeah, that's another way. So there are different ways to do that. So I am doing one way here. The project actually talks about that way already. You can also do u plus r if you want to do set give read permission to the owner, then you can say u plus r, I believe, and then the file name. Okay, so this is another way of setting these permissions or changing them. You want to remove the read permission that's already there, I believe you say u minus r. I think if you and then that's what it is. You can remove by doing minus and add by putting a plus. Go through the project of it. That's another way of doing it.
But I'm saying, was there a specific reason why they put the numbers, or just because?
The numbers, actually that's what internally happens. If you see, it's an exponent of 2. Yeah. Right? So internally it's stored as 3 bits. The execute is the least significant bit, the write is the most significant bit. You see it's 1, 2 and 4. So this is stored as the least significant bit, this is stored as the most significant bit, and it's exponents of 2. So this way you can directly access those bits. And even if you do this, this is what is happening. Internally that's how it's done. Okay? So like files here, folders have, folders means directories, also have permissions in Unix. So if you set, so a folder is also stored like a file, at least for Unix. Okay? So if you set a read permission for a folder, okay, what it means is, if you set a read permission for a file, you could read the file, right? If you set a read permission for a folder, it means you could list the contents of the folder. Which means what? Like in Unix, if you come across the ls command, if you use that, it lists you all the files in that directory. So if you have read permission, you can list all the files in that directory only if you have read permission on that folder, on that directory. Okay? If you have write permissions on that folder, you could create new files in that folder. So again, in the project, you will do all these things. So if you don't have write permission in a folder, you cannot create any new files under that folder. Okay? If you have execute permission for a folder, you could kind of traverse that folder. Okay? So for example, there is a user Bob who is working from this directory, and there is a user Alice who is in this directory, and she has a file by name readme.txt. And Bob wants to read that file. So in order to read that file located in a different directory, Bob has to have what? The execute permission to this folder called Alice. And then once he visits that folder, he has to be able to open this file and read it, right? So he has to have a read permission. So you may think that Alice may think, okay, I'll just give, say Bob belongs to the others group, right? So she may think she can give read permission to the others group and everyone can read that file. No. She has to also make sure that she gives what? The execute permission to the others for what? The folder Alice. See that basic thing? So when you want to say as a user, you have a file and you want everyone else to read that file, okay? So it's not sufficient for you to just do what? Give read permission to the others group, to the others to read that file. You should be able to make sure that others can visit that folder and then read that file, right? If Bob wants to read that file, he has to first be able to visit Alice, right? That folder Alice. So Alice should make sure that the others have execute permission on that file. So these are two things she has to do. It's not sufficient to just give read permission to your file. You should make sure the other users can visit your folder and then read that file. Okay?
You mean execute on the folder or read on
Execute
the
on the folder.
Not read.
Not read. Okay, because if you give read, Bob can see all the files, not see in the sense that he can list the contents of the folder Alice. You don't want to give that extra privilege to Bob. All you want to do is enable Bob to be able to read that file readme.txt stored in the folder Alice. Right? So you want to give him the execute permission so that he can go up to this path, and then once he is on this path, you need him to be able to read only this file. So just give read permission for this file. Okay? Any question?
So any other files within the Alice folder you would have?
He won't be able to see what are the other files there because he doesn't have read permission on that folder Alice. He has only the execute permission on that folder, so he can just visit that path or that folder, but he cannot see what are the files there, and or he cannot write or create a new file in that folder or delete a file in that folder. If you have write permission, you can delete a file or add a file, you can do whatever you want. That's the most kind of riskiest thing you do. If you give write permission to some other user, they can do whatever they want.
Okay, so just because you can execute on a file, doesn't mean you can read all the files within that folder.
If you have execute permission, the only thing you can do is you can kind of, you have worked on CD and all these things, right? The change directory command. So let's say you are currently under home, user and Bob. Okay, so there's something called the present working directory in Unix. If you type pwd, you should get that. So now let's say you want to read that file of Alice. So what you should do, you say cd /home/user/Alice, and it will take you to that folder, this folder Alice. So now you are in the folder. Okay, so if you type pwd, it will display like this. So now you try to say run an ls command. Since now you're running as Bob and Bob doesn't have read permission on the Alice folder, you will get an error message, permission denied or whatever it is. And he cannot do anything except what? Read the file readme.txt. He cannot read any other file also because he doesn't have any other read permission on any other file. Okay? Is that clear? So now going back a little bit on how passwords are created and stored with all the dictionary tags, we'll look at it from the Unix point of view now. So how the user, I think I've told before, Unix stores, not anymore all the time, but some time back they used to store the encrypted version of user passwords in a file called pwd, I think it is, right? A password.
Password.
etc/password.
Yeah.
So this is the name of the file in which you have information something like this. So let me show you that how it is stored. So So this etc slash password etc is a folder and password is a file. So it used to have entries like this for every user. And the first is actually username. The second is actually the encrypted version of user password. The third is the user ID. The fourth is the group ID, who the user belongs to. The fifth is the full name of the user. This is the user name and or user account name. And this is the user full name. Okay. And this is the you see slash u slash virtual, which is basically the when you log into the system, this is the directory to which it gets logged into. Every user will have a default directory to which they log in at the time of login. And this is like Unix, we have different shells, K shell, C shell, Bourne shell, and all those things. So this is again for each user you can set what should be the default shell you get logged into every time you log in. So all this information is stored in this password file. And this is publicly accessible. The reason why it's publicly accessible is there are several other programs in Unix or applications that use this file. Because internally each user is kept track of using this user ID. They are not kept track of using the username. So we may think we have a username, so we are kept track based on that. But the username is basically for identification purpose. Internally, every user and every group belonging to which users belong to are kept track of based on the user ID and group ID. But there are certain application programs that needs to know what is the username according to that user ID. So this is the only file that has mapping between the user ID and username. So this file has to be accessible to all the applications that needs to know this mapping. So that's why this is kind of allowed for everyone else to look at this. Because if you write an application that needs to know what is the user ID for the user or vice versa, then